This conference will now be recorded.
Hello, everybody. Jordan Girth here from the National Weather Service Office of Observations. Thank you for joining us for the Satellite Book Club Seminar Series. This is session number 54. Appreciate you taking time out of your busy day to be with us. Active weather across the country. Today's presentation, ABI fire detection, the Mesoscale fire detection and characterization algorithm, brought to you by Chris Schmidt, our presenter today. He is a researcher at the Cooperative Institute for Meteorological Studies, University of Wisconsin-Madison. Our facilitator is Todd Lindley, the Science and Operations Officer at the Weather Service Forecast Office in Norman, Oklahoma. Just a few reminders before we get started today that the session is being recorded, so you can share the link with your colleagues if they aren't able to be with us today. And there will be an opportunity for Q&A after the presentation. So please post your questions in the chat room and we will try to field them in the order they are asked. We're always looking for future presenters, so if you have an application you'd like to share with your colleagues, please get in touch with us. And if you're looking for training, we've got Brian Mata, the Office of the Chief Learning Officer, as well as our Cooperative Institute trainers that can take your information, that can provide information and take your questions regarding that. Just like to thank the Tower S team, particularly Krishad Bowman, Lee Byerly, for their support of all the behind the scenes work. The Office of the Chief Learning Officer, GOES-R and JPSS programs for getting us to this point, over a year of Satellite Book Club seminars. Without further ado, I'd like to introduce Chris. As I already mentioned, is a researcher at SIMS UW Madison. He started with the biomass burning team in 2002, tasked with masking the WFABBA making the WFABBA operational, and has been the algorithm lead for the fire detection and characterization algorithm for the ABI. Chris is working on updates to the algorithm and lining up resources to develop a next generation fire algorithm. Chris is a repeat presenter to the Satellite Book Club, so welcome back, Chris. Glad you could be with us.
Thank you, Jordan. As he said, I've been doing this for a while. This presentation is really going to focus on two things that have appeared in AOPS recently, or with the recent update. The mesoscale data that NOAA is now producing at the mesoscale cadence, I should say, and the mask, the fire metadata mask that has been invisible to forecasters for the last few years. I'm also posting in the chat a set of links. This is preventative medicine, if you will. There's some animations, and I know sometimes those can be choppy, so I've put the links to those animations in order in the chat, so you can click on those if we have problems as we go along. And I'm going to turn off my camera now that you've seen what I look like to help preserve bandwidth. So we go next slide. Oh, and I should say too that if you're interested in some of the background that I don't cover today, you can always ask or check out the presentation from last year. Or my link does include, the link at the bottom to the channel does include 2 AMS presentations from this year. Since we had to record everything, I figured I might as well reuse it. So ABI fire detection is actually based on the fire detection for the old GOES satellites. It was known as the Wildfire Automated Biomass Burning Algorithm, the WFABBA, and I still call it that when it's coming out of Madison. When it's coming out of NOAA, we call it the FDCA, the Fire Detection and Characterization Algorithm. They are, for all intents and purposes, at this time, the same thing. It provides fire detections, fire radiative power, fire size, and fire temperature at 2-kilometer resolution for all ABI scans now officially through NOAA, the full disk, the CONUS, and all the mesoscans. So you have a flood of data to play with. This loop, which is playing pretty nicely actually, is all 16 bands from ABI for the East Troublesome Fire last October. And what I've done is I've scaled the data in each panel to maximize the contrast. And the reason I did that is to help show some things off. Well, first of all, the fire, as you can see in the middle, in some cases it's white for the short wave, and for the IR it looks dark. Since dark is hot in the IR in our usual presentation. You can see the fire shows up in most of the bands. Intense fires do that. This one, in fact, pretty much the only 2 bands it doesn't show up in are bands 1 and 2. And arguably there are times where some of these actual wildfires even show up in band 2 because their signal is just that strong. However, when we do fire detection, we really focus on band 7, the 3.9, and a long wave band such as 11.2, or these days also the 10.3 for reasons that relate to GOES 17's health issues. So going on to the next slide. Oh, we also use the visible red band. How do we do fire characterization? The detection is important, but some people need the characteristics of the fire as well. And the general approach is twofold. The traditional way to do things was to try to calculate the fire and size using the Dozier method. It's two simultaneous equations are there on the top right. And using the 4 and 11 micron data and a couple other pieces of information to try to define what the fire temperature and pixel fraction are. Seems like a really good idea on the surface. It works okay, but it's not great. We need more information to really lock down those values, and really temperature and size represent a hypothetical fire that would produce the same signal. They don't tell you what the real size and real temperature of the fire is. It's really more useful for modeling, and I strongly discourage those in operational settings from reporting fire and size, because it really doesn't mean what it seems like it means. Rather, you want to use the fire radiative power if you want to try to provide the intensity estimate in some fashion. You can use it as a proxy. And I'm not claiming that the value itself in absolute sense is correct. In fact, I'm almost certain it isn't, but the trends are good. And so you can at least rely on that, say it's intensifying or not. Now, it's not off by an order of magnitude per se, but I wouldn't argue that it's accurate to within more than 50% at best. Go to the next slide. So we'll look at the East Troublesome fire again, just to show you what the product can look like. Here I've got basically the geocolor is that left panel. It's basically Steve Miller's geocolor. Hi, Steve, I see you were there. And but that was created with GeoToGrid, so it may vary slightly from the one you see in AWEPS and elsewhere. The second panel is the 3.9 micron. That's also been scaled again to help highlight the details of the fire. Then there's the fire mask, and then we have the fire radiative power field. And so I'll just let this go through one more time. And if you're really eagle-eyed, you might see some weird things going on, which we'll talk about in the next slide, like weird haziness around the fire. If we can go to that next slide, I wanted to highlight this because it happened a few times last year, and I'm sure it's going to happen more as we get bigger and bigger fires. There are times where you see a warm halo around a fire, and it can look like maybe it's hot air, or maybe it's just the smoke is really hot, or maybe it's just scattering through a cloud. And that does happen. You can kind of see the scattering through the clouds and smoke happening in this 3.9 micron example. But sometimes it's actually a reflection of the 3.9 micron radiation off of nearby water clouds. And so I noticed this in Oregon, and I noticed this in Colorado last year. And if you look at that 0.47 panel, it's kind of in the top middle. I've highlighted this little water cloud, and you can tell it's a cloud because it's cold in the 6.2 there. It's also shown. And if you look at the other long wave IRs, it's cold there too. It shows up as warm in the 3.9. It doesn't show up in the other short waves that show the fire signal, even the ones that show kind of a blurriness from scattering through cloud and smoke. And so this is something just to be aware of when you're monitoring fires. It doesn't, if you see that heat signature, it doesn't mean the fire is spread necessarily. And it'll even trick the algorithm sometimes. You can see the algorithm did pick up a little bit of that as an actual detection. And that's one of those little details you catch after a while. And it's definitely a challenging issue. I can't say if we'll ever, at any time soon anyway, be filtering that out for you in the product, but something to be aware of as you're monitoring it in real time. Next slide. So next I'll go into the looking at this in AWEPS and talking about the Meso product in AWEPS as well as the mask in AWEPS. And so the mask is not just, unlike the characteristics, it gives you 6 different categories about the fires. There are processed fires, which are the highest confidence. They all have their FRPs, their size, and their temperatures, or at least they should, presuming there's no bugs anywhere in the chain. Saturated fires are the highest confidence, or another high confidence fire. The sensor was saturated, however, so if there's an FRP, which there usually is, but not 100% of the time, it's a low-end estimate. Cloud-covered fires are exactly what they sound like. We think it's a fire, we're pretty sure it's a fire, but the reflection over the fire in band 2 is also pretty high. And that could be due to clouds, smoke, or bright surfaces. That happens too, unfortunately, because we don't apply a formal cloud mask in this algorithm. Our goal is to get the data out as fast as possible, so we have a simplified cloud screen that we use in order to just get our job done and move it on. For those cloud-covered fires, FRP may or may not be available. High probability fires are, they're lower confidence than the processed. They'll usually have FRP. You may sometimes see a temperature, but I wouldn't worry about that, like I said. Medium probability fires are another step down. You'll have more false positives in here. They'll often, but not always, have FRP. And low probability fires, and I've colored these the way the masks usually color them, by the way, are the lowest possibility. Most false positives live here. Most of them don't have FRP. And if you don't have FRP with a low probability fire, it's almost certainly a false positive. So the examples we'll look at are drawn from recent events, one from May and a couple from last week. And we'll just go through those now. Next slide, please. So this is just an example of what things look like in AWIPS, again, from last week over Southeast Utah, just kind of querying some of the fires. We loaded up, Lee Byerly, thank you for your help, loaded up the masks, and I loaded up the mask and the products and stacked them up on top of the viz. I like to use the viz for reasons that may become apparent as we go forward. But here we're just showing what an example of one fire, what you get out of it. You get the processed fire category, you get a temperature, FRP, and a size in meters squared, and then there's the viz on below that. And we'll go to the next slide. We'll have a different fire that we've queried, a high probability, and here you see we only have FRP, and the other two products aren't included. The next slide will be yet another classification. This is cloudy at a different time step. A pixel got called cloudy. In this case, we can't see it, but there's the albedo is 12.2% readout there. That's saying it got over the threshold for looking like it was cloud covered. And it may well have been smoke, because in this case, we did see smoke. And there's no properties for this fire. I didn't delve into why specifically it didn't have an FRP. Like I said, sometimes I do, sometimes I don't. That just depends on details in the algorithm. Next slide. Now this is a true positive fire. In fact, I think it was the same fire just early on. Low probability, however, and just showing what that looked like. You get this one little pixel out in the middle of nowhere, has an elevated temperature, 59.5 C, and looking at a nearby background pixel on the next slide. And that was 47 C, so about 12K or 12K/C lower than the fire. And so that's just fairly elevated, and it's calling it low probability, probably because there's also a fair amount of reflection on the surface, bringing up the brightness temperatures in the 4 micron in a lot of places nearby. Next slide. So looking at an example over eastern Iowa back in May. This was just one we grabbed randomly. And all these were examples I grabbed randomly, by the way. We didn't dig and look for specific cases. I don't have names for these things. We just looked at, hey, there's a fire, let's look at it. This was a day, it was a red flag day, I believe, in Iowa. So there was a risk of fire spreading rapidly. And you can see this is a very short loop. It's not even really an hour long, barely over an hour long. And yet you get a fire and some clouds popping up, or a fire and some smoke popping up out of it. A couple other things happening in the scene too. There is a small fire that pops in and out, and there's also a false positive due to cloud, which we'll look at coming up here on the next slide. Here's the smoke plume. So if you look at the loop carefully, you can see the smoke plume coming off of this. Again, it shows up big. It shows up big, and it's a small fire, but it's still a small fire. It didn't last very long, so it was probably grass fire that burned itself out pretty quick. Next slide. So there I'm highlighting a small water cloud. It's a cloud, you can see it's a cloud, but on the next slide, it got picked up as a fire. And this happens, unfortunately, frequently. It's something we're working on. And it's because water clouds reflect 3.9 micron radiation. And for various reasons, the algorithm is not yet smart enough to get rid of all of them. So you will see that, but this is why I like using the viz. It really highlights quickly where those cases are popping up when you look at a viz animation. You may notice I'm not using the fire temperature RGB. I just don't like it that much. I know a lot of people do. Certainly, there was a presentation about it last week. Jorel's great presentation last week did include discussion of it. I know it's very useful for some folks. but I tend to look for the smaller signals, and the fire temperature RGB kind of hides the smaller signals. So next slide. So we're looking at an example of GOES 16 and 17, comparing 5-minute GOES 16 and 1-minute GOES 17. Sorry, I was noticing the chat was suddenly blew up. And here, there's a couple things going on. First of all, we're looking at the fire from 2 different satellites and seeing how they both saw it. And also you can see that the pixels are parallelograms in different orientations, which you're familiar with if you used AWIPS and looked at data. But in this case, you get to see kind of side by side what that looks like. So we can go to the next slide for just highlighting which is which. So those parallelograms oriented to the upper right are GOES 17, and the ones oriented to the upper left are GOES 16. The colors in this case were just to associate with pixels that don't mean anything other than the fire class at that particular moment. Next slide. So here we have the animation. And like I said, the GOES 16 is every 5 minutes and GOES 17 is every minute. And you'll see much more variation in the GOES 17 data because it is coming every minute. Some of that variation is real, it's the fire. A little bit of it is technical details about how the instrument works, which we won't get into here. They do matter, but most of the variation is actually in the fire itself. They really do move that and change that fast. There are some data dropouts, were just an unfortunate reality that day. It's just what happens. But you can see that these footprints look very different where these things are. And it's not that the satellite's confused, it's just the way we navigate our data with GOES. We don't terrain correct our data at all, but I'll talk about that a little bit after the next few slides. I'll let this finish first before we, oh, that's fine, we can keep going. So I wanna highlight just an early period, but since the animation worked pretty well, we don't need to spend a lot of time on it. Go to the next slide. So this is just early on. GOES 16 actually had a better representation of it than GOES 17, and this can be for a number of reasons. Again, this is details about how the detector, the sampling is hitting the fire is probably the biggest reason why there's a difference here. And just step through to the next slide. See the category has changed. We're going minute by minute, synced with GOES 17, and so the category changed for GOES 17, and we can step forward, and oh, it changed again, step forward. And now GOES 16 loses it on the 1921Z scan, which is now folded in, and we can keep going forward, but GOES 17 holds it, keeps holding it, step forward again, raises the possibility, step forward again, and now GOES 16, step forward a few minutes there, and GOES 16 picks it up again. So now here's another example. I just wanted to show the false positives from water clouds one more time, but a more egregious example. This is again last Thursday. So Thursday, Friday data is what we were looking at when we built these loops. And this is again just over Utah and small water clouds, and occasionally, you know, certain size, certain reflectivity of these clouds, and they pop up as false positives. And so you'll see that happen, and it happens more with the meso than it does with the CONUS and the full disk, unfortunately. But with the meso, you can see that it just comes and goes really quickly. Next slide. And so that's just in one case, we had a couple next to each other at the same time. Next slide, please. So speaking of terrain effects, we're working on this. I was hoping to have a really pretty example to show where we could show you how this would be corrected, but instead what I've got is an example of the correction in progress. Here we have a location in the Bitterroots that it's plotted on top of a DEM, so it's just elevation data, and a location that where both satellites think they're seeing the same thing in red. It's roughly, they think they're roughly looking at the same spot. The blue, however, is what they're actually seeing. That's the territory they're actually seeing. And the point of this is to show first the offset that everybody's familiar with, but also how convoluted the terrain can make the footprint. Now, granted, due to physics and diffraction, the footprint isn't a rectangle or a parallelogram. It's more complicated than that, but you know, the basic, most of the energy is coming out of that red or blue area, yellow being just the overlap between the two. And this is something that is of concern for a lot of reasons. One, you can see we've moved between mountains just by correcting, which has real world impacts. It also illustrates just how important terrain shadowing can be. And that's something that eventually I want to be able to produce, is a map of figure out where we can't see with ABI for fires, because we've had cases where folks have seen fires in one satellite and no hint of it in the other. They can even be decent sized fires, and it's literally because the mountain's in the way. So next slide. Just some common questions. Why do we see different fires? Terrain is the most common cause. There's also things about viewing geometry, where clouds are, can affect things. And even like I said, details about how the samples are being processed can affect how strong a fire signal looks. And so those all can affect why satellites are different. So you can't really say that one is seeing a fire, the other isn't, therefore it isn't there. You have to pay more attention to the context. How small of a fire can ABI see? Well, the human eye can pick up really small fires. We can see house scale. The algorithms are less sensitive than that. I say algorithms because the FDCA isn't the only one out there. But we've picked up single acre fires. In fact, I saw an example just yesterday of that happening in California. Didn't have time to put it in here. We've even had small gas flares and things like that trigger the algorithm. As far as known issues go, false positives are a problem. They're a well-known problem. Reflections are the biggest source, not the only source, but by far the biggest source, from persistent anomalies, which we're working on masking out, such as solar farms, other bright surfaces, and we've got the reflections off of water clouds I've talked about. You can have thermal sources as well, things that look warm but are for various reasons, like say it's a refinery, say it's that one field that's been plowed in the spring and there's a whole bunch nearby that haven't been, and so you get the warm soil, the soil warming up differently. Old burn scars can look warm enough to trigger fire alarms. But by far the biggest annoyance for folks are reflections causing false positives. Although of course it depends on your use, how you're using the data. Tips or guidelines for how to, thresholds to apply to use the data. I would say focus on the mask and the FRP. Again, just ignore the size and temperature for most purposes in operational context. They're just misleading. The FRPs can range pretty low and still be real. If you want to be pretty dang confident, you can screen out at say 75 megawatts. You will throw out real fires, but you'll get rid of the vast majority of false positives. That number can also vary by region. And I believe this is one more slide. Yep, that's it. So obviously, if there are any questions, please ask away. We've got some other pretty pictures at the end if we want to talk about the Kincaid fire or solar farms. Otherwise, special thanks to Chad and Todd for their work in making the mesos and the fire mask and AWIPS happen, as well as many others who made the mesos happen, like Tom Ferroli from the Pro team and others. Lee Byerly, thank you again for your help with making these masks. And I love AWIPS in the cloud and can't wait until I can use it more regularly. And that GoWhisk.edu link will take you, it's in the chat, but it will take you to the page where I've been stashing all my videos.
Well, thank you, Chris. That was an excellent presentation. And yeah, thanks to everyone that actually contributed to make the FDC data available in the mesos. That's a big step forward that was kind of lacking. That was a big service gap, I think, for a number of years there. So yes, thanks, Chris. And I guess I'd like to encourage everyone to participate in an upcoming question and answer section and discussion, and stay on for that. And also to fill out the survey that has just been posted in the chat for feedback. But first, we do have a little bit of housekeeping. I need to let you know that next week, a week from today, on Thursday, June the 24th at high noon Eastern Time, Jeff Hawkins, formerly from the Naval Research Lab, will discuss the satellite-based tropical cyclone surveillance since Katrina, an exciting era. So be sure to come back for that presentation next week. And also encourage all of our attendees to contact the Tower S team, which includes Lee Byerly and Kashad Bowman, for any questions about the SBC or for configuration of satellite products, and that more information will follow from the Tower S team. So with that, I'd like to remind everyone to submit questions in either the chat room here or to indicate somehow in the chat that you want to ask a question verbally, and we'll try to get to those. So I actually see a few questions coming in already, Chris. The first one is from Ryan Walbrin. Can ABI learn, quote unquote, where solar farms and other common false positives occur? Man, that's been a big topic lately.
Yeah, we're working on that. We're approaching it as a persistent anomaly mask, and right now discussing how we're going to actually implement that, because you don't just flag a pixel and say, well, there's a solar farm here, and we're just going to ignore it. You can't do that, because the solar farm is only going to trigger at certain times a day, often only a 15-minute window. But as some people have found out the hard way, you can actually have a farm burn. So we don't want to exclude the real fires that occur there. So we're working on how to not only just flag something as, yeah, this could be a solar farm, but also that, yeah, this is probably just a reflection. And of course, it's not as simple as, well, it's just the right time of day, because everybody orients their panels differently. So in some regions, they're all pretty consistent because it's the same utilities putting up the same things. Like in Minnesota, there's dozens of farms going up in Minnesota, driving people nuts as they start seeing these things, don't understand what's happening. And it's because there's an incentive program in Minnesota and they're building them like crazy. So yeah, we're working on a persistent anomaly mask. There'll be different variations of that coming out over the next few months and years. A lot of thanks to Yvonne Cesar and Wilfred Schroeder, especially Wilfred, for his work on that so far, and it will be part of Fire Products in the future.
Awesome. Good to hear that, Chris. We have another question from Tim Barker. Can you speak to why the GOES 17 CONUS and FD come via data delivery, but the GOES 17 Mesos come via a different mechanism? And actually, do they come via SBN or regional LDMs?
I am not the expert to answer that question. Lee has spoken to it in the chat. He said the GOES 17 Meso Fire products are newly available and initially flowing out over regional LDM as our GOES 16, while other flow mechanisms get coordinated. So
Thank
maybe
you,
somebody
Lee,
else can
for
speak to that.
thanks, Lee, for answering that and providing that insight there. I believe Chad Gravel at Southern Region Headquarters has a question.
Yeah, hi everyone. And this is really this is sort of for Todd, actually. I'm wondering if you could, Todd, talk about the use case that we've discussed on using this 1-minute fire mass data. Because we didn't really get into that here, but I think it might be good for people to hear about why it's so important. So, and the one that I'm referencing, Todd, is, for the hotspot notification tool, and using this data to help provide a confidence to that existing, I won't call it a product, but that existing IDSS mechanism, basically. So you're the expert there, Todd. So I thought that maybe you could chime in on that for everyone, especially for the NESDIS folks.
Yeah, you bet, Chad, and thanks for that kind of lead in there, even though that was unplanned. I did have some follow-up questions for Chris that would maybe help start the conversation in that direction. So like Chad said, there is some enhanced IDSS or impact-based decision support that we do from the field, where some of our partners have requested that we let them know, when we see under certain conditions that when we see new fires ignite. And so we've not really had a good opportunity in Oklahoma to use this in real-time operations just yet. Chad, you and I kind of did a informal evaluation, I guess you could say, during the spring when they burned the Flint Hills in south central Kansas and northeast Oklahoma, evaluating it on a few days when there was a lot of prescribed fire. So we kind of have an idea of the importance this might play in operations. And like Chris said, there are some pitfalls, I guess you could say, to the FDCA as far as using it operationally. Physically, the values don't make a lot of sense. There's some delay in triggering the derived products, especially fire size, fire temperature, fire radiative power. They have to meet certain thresholds of confidence. Where the masks may come in useful is they appear, you get a signal regardless of where the fire ranks on that confidence spectrum, and then whether it's under cloud, thought to be under cloud, or whatever the characterization is. So you get some signal almost immediately as soon as, in the past, it appeared practitioners, forecasters could identify fires much earlier than the FDCA did, just by visually inspecting the 3.9 shortwave IR. And now that fire might show up immediately or within a minute or two as a low confidence fire. And yeah, that adds a little uncertainty, but when you pair it together with the visual interrogation of the base data, a forecaster would be able to identify that more definitively. And I think Chad, where this really is important is it could kind of level the playing field, right, among forecasters and among WFOs. Maybe not all WFOs are as accustomed to monitoring the 1 minute base data as others. Some of the comparisons been made. Well, in Oklahoma, you look at a lot of supercell and severe convection via radar and satellite all the time. You're very well versed in remote sensing. I think all meteorologists are very well versed in remote sensing, but some definitely do it more routinely as part of their mesoanalysis and their real-time weather watch than others. So this could help kind of level the playing field. Chad, does that kind of go in the right direction?
Yeah, I think so. And one of the things I believe your EMs and your state partners have requested is a confidence for these hotspot notifications, correct? And we haven't been able to do that. And this provides us a way to give them a confidence, even if it's low, medium, high. That's still better than nothing. And it's better than the human saying, well, I think this is a hot spot, a high confidence fire based on my expertise. And that expertise, unfortunately, will vary across, someone that's been looking at this for 5 years versus the new Met that maybe has only been looking at it a year. And this kind of, I think we've talked about, and we've used the words level the playing field on providing confidence information.
Yeah, that's exactly right, Chad. And the most frequent feedback we get from our fire partners is that they want some measure of confidence that that signal we're telling them about is actually a wildfire. And of course, it's really hard to do that. In fact, we don't want our forecasters doing that. Instead, what we've done is provide proxies for confidence, like, well, the weather conditions there are extremely critical, and the detection method was 1 minute, go 17 versus 5 minute versus, a plume seen on radar. We've given them things we actually know, facts we know, and they can have inferred confidence from that. So one of my questions for Chris was actually, we have these characterizations of low, moderate, high confidence. Are there explicit like percentile or thresholds that correlate to those, Chris, or how are those determined?
I wouldn't call it, there's not really percentile correlations. At their root, it comes down to how strong the signal is relative to the background and relative to the variation around it. So it's really signal strength. But I'm hedging because there's not a strict rule about that. It's all contextual. There's parameters like 2.5 standard deviations or 3 standard deviations, or things like that. But it gets really deep into the weeds really fast. Yeah. So.
Yeah, good to know, Chris. And we do have another question that's popped in the chat here from Mike Pavlonis. He says, why provide the fire temperature and area if the interpretation is too nuanced for operational applications? Are they being distributed because there's a requirement written in stone, basically? So I'll let you, Chris, tackle that one.
I will be diplomatic about why this happened. It is the way it is because it was the way it was. When the ABI requirements were originally written, they took the GOES requirements as far as what the products were and just translated them straight over. So we produced FRP size and temperature under old GOES back when we were relatively anonymous, and then With NUGOs, that was the requirement. And so that was in the file. It's unfortunate that when things went into AWIPS, basically size and temperature is what people saw first, and FRP, and then they only saw it for a very small fraction of the fires initially. I widened the scale for FRP just so you could see more fires, and thankfully now we have the mask. But if we could go back and do it again, I would not have put size and temperature as they are currently done anyway in this product. Now, having said that, could size and temperature ever be a reliable product? Yes. Doing more fancy math and actually using more bands, but again, this gets into the history of how we got here. And that's why I say now, if you want intensity, look at FRP, and the mask is great for telling you everything.
So Todd, I'd like to chime in for a second, and this is I understand the world that we live in here. That being said, it would be nice, and maybe this is like Chad's fantasy land, where and people are going to probably laugh at this, right? Because Chad, you don't understand requirements. I do, but at the same time, it's almost like when we learn over the year, we have to do this so far in advance, right? And when we learn things over the years, especially once we start getting our hands on the new data, it would be nice to be able to call an audible, right? So that we can, maybe not have to use bandwidth or not have to focus resources on something, but we're to absolutely be able to refocus our resources on something new. Things that, Mike, Pavlonis, I know that you're working on. I just wish the infrastructure would be there that would allow us to maybe have a little wiggle room per se. And again, it's probably Chad's fantasy land, but maybe you guys are all thinking about that just to make us a little more agile so we're not so handcuffed by, these requirements. I guess that's all I'll say on that. But if anyone else wants to chime in, I'd love to hear your thoughts on, how crazy I am.
Well, I should add that the size and temperature did have users who, verified users who requested it. It's not like it was just tossed out there.
The modelers, right, Chris? I mean, isn't that
Yeah,
a
the
big part
modeling
of it?
community in particular
Yeah.
who had been using it wanted to keep using it, and that's fine. This comes down to the question of do all users need to get exactly the same files? That's a whole different issue.
Yeah, I think this is an important topic, and I don't think you're crazy, Chad. It was really very eye-opening to me when, for those on the call that may not know, Chad, Chris, and I, and other contributors published a paper on the GOES 17 detection of the Kincaid fire in Northern California, and it was very eye-opening to me in that process to see, how those values really don't have a lot of physical correlation at all to fire behavior, and that kind of brings me to characteristics. That kind of brings me to another question I had, and then I'll stop asking my questions, Chris. But have you been able to correlate fire radiative power versus like shortwave IR, 3.9 shortwave IR brightness temperature? And I know, I feel like there's not a lot of science that has been put into or invested yet on, how the signals we're seeing in remote sensing correlate to potential extreme fire behavior. So I'm curious if you have a preference for using one metric over the other, or if you've seen evidence that that you can remotely see signals that are at least consistent with times that we know we have extreme fire behavior occurring.
Oh yeah, well, FRP, the fire radiative power, is directly related to the difference between the fire and the background. So it's sensitive to how you've estimated your background and what however you've tried to account for attenuation, if at all. But I'm skeptical of how accurate any method has been with satellites, at least for these large footprint satellites, in actually getting the value, quote, right, unquote, on an absolute sense. We can model it and say we've got the right techniques perhaps, but well, we can model it and say we got the right techniques, but how accurate are our models? And I say that because you're talking about a small subpixel feature that's really hot, looking at it with essentially a fuzzy lens, because no pixel is perfect. You've got an inherent error right off the bat, depending on the diffraction, the airy spot, all these telescope details that we don't even have publicly available, all the information on how to calculate those things. That gives an inherent error to these measurements, which for most things is not an issue because it's large scale. It's bigger. But when you're talking about 1% of the pixel, it matters where that 1% lands in the pixel. So those are things that we just don't have a very good estimate of. But in general, the trends are reliable, and certainly the difference between a small fire, medium fire, or large fire are very evident. So I think FRP is reliable and very reliable in terms of trend monitoring and watching how things blow up. And a lot of users who've been using FRP data are not so concerned with whether or not it's absolutely accurate so much as the trends are accurate, because as one person put it, I just scale everything anyway. Again, it varies from user to user. Some really want it to be perfectly accurate. That's fine. Other modelers are happy to throw scaling factors in because everything else has scaling factors too. So I don't know if that covers your question, but I see there was one more from Mike asking why have it in AWIPS momentum. Why have those things in AWIPS? It's the bureaucracy and the momentum. It's how things have worked. That's the answer I've got anyway.
Yeah, thanks, Chris. I think that does answer my question, and I think it's so important to look at the trends. We've even used in AWIPS I think it's called the tracking meteogram to look at the sudden jumps in shortwave IR brightness, temperature, and fire radiative power to help interrogate some of these fires and see how they differ in different environments. So I know we wanted to try to wrap this up right around 11:45, but I see Jordan had a couple of questions he indicated, and I'm supposed to throw it back to him at the end anyway. So Jordan, do you want to ask now?
Yeah, I'll just ask a quick question. Maybe this is for both you, Todd, and Chris. But Google has come out with some fire boundary information on their site, and I'm just curious if you've heard anything from your partners, emergency managers, others that may be looking at that, and how you're reconciling that with the information that you're looking at related to GOES. It is the Google outline is based on GOES. It's an algorithm, but I didn't know if that was starting to enter into what you were hearing from your customers and partners.
I haven't heard much about it from people other than they know it exists, and I don't know that Google is doing any terrain correction. Last time I talked to them, they weren't. And so the fact that they're getting it sort of right is probably related to the fact that they're using both satellites and looking at large events. And so they kind of just lands in the right spot by averaging. But I haven't heard much about it otherwise as far as people using it.
Yeah, and on the operational side, I would say I've heard zero feedback from our fire partners here in the Southern Plains as far as them using it. And from what I understand from Google's documentation, it's a very crude method. Like you said, Jordan, it's relying on the GOES data. So my guess is they're overestimating the footprint of the fire. But I think it's important to point out that they're doing something, right? I mean, they're providing a product and filling a service gap, and maybe we should take note of that.
All right, thank you so much. And thank you, Todd, for moderating, and thank you, Chris, for your presentation today. Just a few reminders before we let everybody go, that once again, next week, we will have Jeff Hawkins at 12 noon Eastern Time, Thursday, June 24th, formerly with the Naval Research Lab, is going to discuss satellite-based tropical cyclone surveillance since Katrina. It's an exciting era. And contact the Tower S team for questions about the Satellite Book Club, or if you have any questions related to the configuration of satellite products, including the products that we discussed today related to fire weather. As always, there'll be more information in an email from the Tower S team. So with that, I will conclude session number 54 of the Satellite Book Club seminar series. For those federal employees, keep an eye on announcements from OPM. I understand that tomorrow may be a federal holiday for people that work Monday through Friday, and maybe some holiday pay for those that are on shift. So with that, take care and hope you'll join us again next week.